So as part of this CASIP, a new sea ice model is being developed, and the idea is that this sea ice model will also get data assimilation capabilities. The idea is behind data assimilation is that you don't know what the true state is, evidently, but that you can have some probability distribution that can give you the true state. And then you combine this probability distribution with observations in the hope that you end up with a probability distribution with a smaller spread. And in an ensemble data assimilation system, this probability distribution is approximated by an ensemble of model runs with the situation just before the combination, the data assimilation with the observation called the background, and the situation just after the assimilation called the analysis. Now, one of the novel features of this sea ice model is that it's going to use a discontinuous Galerkin numerical core, and as was already explained in the previous presentation, that means that the model solution in each grid cell is a linear combination of basis functions, in this case Legendre polynomials, and that is different from the current generation of models like finite volume models in which the solution in each grid cell is assumed to be constant. Now there are some known issues with data assimilation, and we looked at whether this structure, which partially resolves the model solution within the grid cells, can be used to address those issues. Those issues are, one, that in finite volume methods one cannot speak about a derivative within a grid cell, so maybe with these discontinuous Galerkin methods it becomes possible to use data assimilation to correct the derivative. Well, the second problem is explained over here. So in black we got some true solution. In blue we got the best fit we can get from a finite volume method, and we got some observations that have uncorrelated errors around truth. But as you can see, the observations on the right hand side of this cell are all above the best finite volume fit, while those on the left hand side are below. In other ways, we now got correlation between the errors in the observations, and this is problematic because previous work has shown that as you decrease the distance between the observations and assimilate more observations, then initially the root mean squared error after data assimilation goes down. But if the observations are spaced very close together and you don't take this correlation into account, they go up again. So we wanted to see whether the DG structure can address this as well, and to test this we used an idealized stochastic model, so there's no physics in here, and what we've done is we generated an ensemble mean as a Fourier series. Then we generated perturbations to that mean. We did it using different spectra, a pink spectra, the power spectrum as function of the wave number shown on the left, which, as this example of the perturbation shows, has a lot of small-scale error, and a red spectrum, which has more large-scale errors. Then we added these perturbations in the ensemble mean, generating ensemble members. We set one of these ensemble members apart as being the truth, from which we sampled observations, and the other ensemble members we treated in two ways. We interpolated them to a uniform grid. This represents our current method, and we projected them onto the DG polynomials. Then we fed them into our data assimilation system and looked at the root mean square error after data assimilation versus the root mean square error before. The ratios of those two are shown over here as function of the number of observations per grid cell, with the blue line being the current generation of models. And what we see is that for low observation density, they perform the same, but for higher observation densities, the ratio is lower for the DG models and keeps decreasing as the number of observations goes up, but there's not much benefit from using DG orders higher than 4. For the derivatives, we don't see much improvement. Now this is for ensemble members with a red spectrum. If we now look at the ensemble results from using a pink spectrum, then we see that the root mean square error ratios are higher in general, but that in this case there is additional reduction can be achieved by using higher DG orders, and in this case there's actually even some deterioration in the derivatives. The third problem we looked into is explained over here. So on the top is the covariance from a 10,000 member ensemble. On the bottom, the same covariance, but now from a 16-member ensemble. And as you can see, you get a lot of noise due to sampling error. And the way that's usually dealt with is by tapering the values off to 0 with distance. But you can imagine that if you got this tapering distance is dependent on the scale in your model, and if you have a multi-scale model like an ICE model, then you should have multiple tapering scales. And the Legendre polynomials shown here on the left might offer you a way to do it, because as you look at the spectrum, you see that the spectrum of the different polynomials peaks at different wavelengths. So the Legendre polynomials constitute a bandpass filter, which can be used to apply different amount of localizations to different scales given by the different Legendre polynomials. Now, what does it look like? So on the right, the covariance, but now of the Legendre coefficients in front of the Legendre polynomials. So these are the spatial covariance of the zeroth order coefficients, spatial covariance of the first order coefficients, spatial covariance between the first and zeroth order coefficients, etc. And you immediately see a strong dependence on the order with the higher order, the covariance for the higher order coefficients being either 0 or strongly diagonal. On the bottom, once again, the covariance from the 16-member ensemble. Yeah. Okay. Now we applied different scale-dependent localization on those coefficients. The results are shown over here. So on the left is localization applied to the current generation of models, and we see that all the negative correlations have been removed, so that's bad. On the right-hand side, it's applied to the DG coefficients, and there's still some negative correlation left, so that suggests that the scale-dependent DG localization performs better. And to quantify that, we looked at the relative error in the covariance as function of the number of ensemble members, and we see that for our scale-dependent localization in green, the error is smaller than for our non-scale dependent localization in orange. So, in conclusion, the ability of DG models to resolve structures within the grid cells allows us to address some problems in data assimilation. We are able to effectively assimilate multiple observations, making better use of satellite sets. We get for free in these models an ability to set up scale-dependent localization. Unfortunately, we couldn't improve the derivatives. And of course, the next step would now be to transfer this into the actual CI's model.